Hello, it's Keith here, and this is lesson 1 of my Risc-V Assembly Programming tutorials. I guess you probably know if you click the video what Risc-V is, but just in case you don't, Risc-V is an open source architecture for developing processors, and what this means is compared to ARM, which is a closed architecture that you have to buy licenses for, anyone can create a Risc-V processor, and unlike ARM, that license can't be taken away from you. So I personally have high hopes for Risc-V, and I would like to see a Risc-V gain a lot of success and potentially take away some of the dominance of the ARM architecture, which, don't get me wrong, I agree is a fantastic processor architecture, but I would love to see an open source solution like Risc-V really gain some ground. So we're going to be looking at it, and the first thing that is quite interesting is that Risc-V is very similar to MIPS to the extent that I learned Risc-V first, and then when I looked at MIPS I realized how similar it was, and I was able to do search and replaces on the commands to get my Risc-V code running on MIPS simulators as well. So if you're familiar with MIPS, this is probably going to look suspiciously familiar to you, but if you're not, it's basically like a more simple version of ARM in a lot of ways. So we're going to be looking at it, and we're going to learn about it, and hopefully you'll have some fun, and you'll be able to feel knowledgeable about this new and interesting architecture Risc-V. Okay. So what do we need to know about Risc-V? Well, the first thing is, unfortunately, there aren't really any game systems or anything using it. I like to generally use a game system like the Game Boy Advance or the Genesis or something to run my code on, so that you can have some hands-on experience and feel like you've actually made something that ran on a real machine. But unfortunately, Risc-V doesn't have a solution that's available to me which we can emulate and do that on. So what we're going to be using today is a simulator. We're going to be using the free RAS simulator, which is a Java-based simulator, and it basically runs as a command line. It's great for testing code. It just doesn't have that real, I've made something that really runs on a real machine feel that I would have liked, but as I say, for learning, it's absolutely fine. Now, Risc-V has an absolutely huge number of registers here, you can see. They're actually all pretty general purpose. There are some recommendations on how you use them, and these recommendations are basically, when you run a subroutine, can you rely on the register containing the same value it did before you run the sub, after you run the sub? And as I say, they're recommendations. Some of them, it's defined if the sub changes them, it has to restore the original value via pushing and popping or something like that. And others, it basically says, well, if you call a subroutine, you can't guarantee the same value is going to be in that register after it's run. But these are all recommendations, so whether we actually do that or not is up to us in a lot of ways. And also, the purpose of these, what they're actually used for, are these to be used to pass parameters or receive parameters? Are these temporary variables? Again, these are all kind of recommendations. The other quite curious thing is these registers have two names. There's the kind of a strict numerical value, which is x0 to x31, and then there's a more descriptive version which you can see here, which is based on their purpose. So the temporaries start with a T, the functions start with an A, and the saved ones start with an S, things like that. Now the interesting one, I think especially, is the 0 register. This can't take a value. It always equates to 0, which obviously 0 is going to be a thing we're going to often want to compare to, and this basically allows us to quickly use a 0 value because it's a hardwired register. There is also a program counter which isn't included in this list. That's a sort of separate register, and this will be used internally a lot for sort of calculating offsets from the current position within the code and things. Now, later versions of the processor do add floating point. This is going to be outside of what I'm covering in my tutorials. I'm only covering the basics. But as I say, there are more registers in later versions, and the original version was 32-bit, but it's been extended to 64-bit and far beyond. The thing with this processor is, because it's an open processor, anyone can add anything they want to it. So there will be various weird revisions that will have quite substantially different functionality, although that is also true of ARM. But as I say, with Risc-V, it's really, because it's an open source architecture, people can add anything they want. We will actually see that as part of the simulator we're using. They've actually added their own commands that are simulated commands. Now, there's a few little bits here with regards to some commands that you might be looking for. I try and keep a list of them on my website, but we're going to see those later on anyway. Now, what I'm going to do first is let's go over to our code and let's actually learn a little bit about the simulator we're going to be using. Okay, so here I've got a bulk minimal example here. You can see it's basically a hello world. We've got our hello world message just here. If I just turn on my zoom here, you can see we've got hello world there. So this is just our very simple example just to show something running. And this is running on our RAS simulator here. And if we just go over to the batch file that I used to run this here, this is my batch file. You can download all of the scripts and the pre-configured environment, so hopefully you can get things started straight away. But if you can't, if you're using a different system, not Windows, you should be able to set this up yourself. You can download the RAS simulator. It's free, it's open source online. It's run in Java, so I've got the jar file here. I've got my Java virtual machine here, and we're just specifying it, and then we're specifying the build file, which is the ASM file. In this case, it's %build file % because I'm running from a batch file. But if you're just using the ASM file, you would just specify that there, and it will run in a command line and show the results to the screen. Okay. So that's our assembler there we're using, or our simulator rather. Let's have a look at the minimal file that we've got here. This is just a very simple getting started that we're going to go over. So we've got an initialization here. Now we need to have a data segment, which is the place that all of our data that we're going to read in, like our hello world message, need to be. There are some quite strong restrictions on this, so we need to have our data in our data segment and our code in the text segment, which it always sounds strange to me, but it's common for what they refer to as text to actually be binary data. I don't know, that's just the way it is. So that's what we're doing here. Now we've got these two sections, and you'll notice we've got these hash symbols, and these are actually the comments on this simulator. I'm used to semicolon. This doesn't use semicolon, it uses hash. The only reason I've put a semicolon after the hash symbol is because it makes the colors look nice on my screen. It's really that superficial. So yeah, the hash is actually the comments on this system. So we've got a hello world string here. We've got a byte 0 after that, which is a 0 termination. The start of our program code is here. We're loading the address of the message here into A0. We are then loading A4 into A7. And we're running this function called eCall, and this is what I said before about anyone can extend RiscV with anything they want. ECall is not a real RiscV command, it's a command within our simulator. Our simulator is taking this command, it's taking the value in A7, and it's interpreting it. And A7 equals 4 means print the string at A0, which is our message, and that's how we're getting our hello world to the screen. You can also see we're then jumping with this J command to this shutdown label. You can see our label here ended with a colon here, and this is loading A7 with the value 10, and this is a different, then running the eCall again, and this is a different command, and this means end the program. So a eCall is basically our it's our firmware calls, if you will, that tells the simulator to do something for us. And there's some really advanced commands in the simulator with regards to debugging and things that I completely don't use. I try to use as little as possible of the operating system. And so I'm also going to try and use as little as possible as the simulator, just because if you're trying to use a different simulator, maybe those commands aren't going to be there. But to be honest, it seems that a lot of this stuff's getting transferred across. And as I say, I ported this to a MIPS system fairly easily, and this kind of seems to be a common thing with these simulators. I would have preferred a real machine to test on, but we didn't have one available to us in this case. So there we go. So that's our minimal example. Now we're going to have a look at the lesson 1 code now. I'll just change that there. So this is the lesson1.asm we're going to be looking at here, and we're going to be going over the code here. Now we've got a macro here. I don't want you to worry about that. There's some, as I say, I'm writing my own code for monitoring the values of registers and things. So just if you can just ignore that, we'll just start all the way here. So what we're doing here is we're loading the return address register here with a 0, just to get an initial point where everything is nice and simply set up. We're then using this function to show the contents of our main registers to the screen here, and we're then branching to this basic maths example here, which is where we're going to start our learning, and we're going to learn how to load immediate values into registers. And this is where we are loading, and there's a hash missing there, where we're loading a value that's specified in line into one of our registers. So if I just run this now, okay, and we're going to discuss each of these lines here. Now, an interesting thing, load immediate, as it's shown here, is not a real command. It's a pseudo operation, and what this means is the assembler is splitting this up into multiple parts. All commands in this RiscV processor are 32 bits, and if we're loading a 32-bit value, we can't load that in a single command, and it's actually split into two parts, and there's a command for loading the low part and there's a command for loading the high part, and they're two separate commands. So this load it immediate that we're specifying here would appear as actual two commands in assembled code, but for our purposes it has the desired effect. It would only be if we were actually looking at the bytecode and trying to work things out that we would know that. But basically what we're doing here is we're loading the decimal value 192 into the register A0. This 0x here, it means hexadecimal. We're loading a hexadecimal value here into A1. I assume you know what hexadecimal means. If you don't, please take a look at my website. I did a tutorial on hexadecimal, decimal, and binary before as part of my Z80 series, but it's all the same. So if you're stuck on what hexadecimal is, you do need to know that. So please take a look at that. The final one here, we're loading an ASCII value here, the letter A into A2 here. So LI, you can see here, the source is on the right, the destination is on the left, so we're loading an immediate value into the register here. And the register being on the left is pretty consistent in all of this. So that's what LI is doing here. So, and you can see those are being represented. Oh, why is this so slow? I don't know why that's so slow there. And so we've loaded these values into our registers, and we can see that in our output over here. So our A0 was loaded with 192, which is C0 in hexadecimal, and you can see that there. The A1 was loaded with FFEEDDCC, and we can see that just there. You can see all of that. And then finally we loaded a letter A into A2, and that's 41 in hexadecimal, and you can see that just there. So there we go. So we've loaded those in. Now, what we did next is we loaded another immediate value into A0 here, and then what we did next is we were going to move that from the register A0 into a different register, and we do that with the MV command for move. So the source is on the right again, and the destination is on the left. So here we're saying move A0 into A1, and of course A0 is unchanged, and then what we're doing next, move A0 into A2, and you can see that over here as well. So we've got A0 equals 01, 02, 03, 04 here. And then we've moved that into A1 and we've moved it into A2. So A1 and A2 now equal A0 because of those two lines there. Okay. Now in these cases we've used immediate values as numbers. We can of course use symbols. We can define a symbol to contain a value. We use this EQV for equivalence here, and we're defining here test symbol to equal 3, and we're loading these immediate values from that test symbol, and you can see those just here. You can see we've loaded those all with 3, so very straightforward there. If you want to use symbols, it makes things a lot clearer in a lot of places. So we've learned how to load an immediate, and we've also learned how to move it into another register. What we're going to do next is we're going to load an immediate value. We're going to load 192 into A0, and then we're going to add and subtract values from that. Now we do that ironically with the add I command. Now we do the add I command even for subtraction, but the value that we add can be negative. Weird, I know, but that's the way things are. So what we're doing here is we're loading 192 into A0, and then we're adding 1 to A0, and we're storing the result in A1. And then what we're doing is we're adding -1 to A0 and storing the result in A2. So again, the source is on the right, in this case one register and an immediate value, and the destination is on the left. So in this case A0 plus A1, in this case A0 -1, and the destinations are on the left here. And you can see that in our values over here. So in this case we loaded A0 with C0 here, which is 192. We loaded that from the immediate. We then added 1 and stored the result in A1, and you can see C1 there, that's +1. And then we subtracted 1 and we stored the result in A2, and you can see BF there in A2. So that's the result of that there. Okay, so that's the second one. The third example we're doing is not using immediates. We're going to use two registers for our addition and subtraction. So again, we're loading 192 in A0. This time we're going to load a value to subtract and add into A2. So we're using hexadecimal 100 here. What we're going to do next is we are going to add A2 to A0 and store the result in A1. And then we're going to subtract, we actually have a subtract command this time, A2 from A0 and store the result in A0. And let's just have a look at that. So we're over here. So you can see here we've loaded the value C0 into A0 here, and we've loaded the value hexadecimal 100 into A2. What we've done next is we have added that hexadecimal 100 to the value in A0 and store that in A1, and you can see that here we've now got 1C0, which is hexadecimal C0 plus hexadecimal 100. And then what we've done is we've subtracted hexadecimal 100, which has turned this value negative, and so you can see that is now a lot of F's and C0 there. So that's our subtraction there. And once again, the format is the same. The destination is on the left and the sources are on the right here. Destination on the left, sources on the right. So those are our first examples of very simple mathematics there. Okay, so that's how we can do some very basic maths there. Next, what we're going to do is we're going to do some reading and writing from memory. So we're going to be using some test data for this. We've got some test data here in our data segment. This has to be separate from the code segment. We can't read and write to the code segment, so we have to have it separately here. We've got some bytes of test data here, and we've got some strings that we're going to use for our test jumps later on. We don't need to worry about those just yet though. So if we just go up here and we just enable this here, and then when we run our example again, we will see some different results. Okay, so what we've done here is we've first outputted the contents of our test data to the screen here. You can see here we've outputted that test data. And then what we're doing next is we are loading the address of test data into A2 here. That's what this LA stands for. So we've loaded that address into A2, and then what we're doing is we're loading a word. Now on this system being a 32-bit system, a word is 32 bits. Now if you're back from the 8-bit days like me, that can be a little bit frustrating. I always think words are 16 bits, but as I say, they're actually the bit size of the processor itself working at native level, which on this system is 32 bits. So loading a word loads 32 bits, and we're loading 32 bits from the address in A2 into the register A0, and you can see that just here. So here we've got A2, which equals this red address here, and that's the address of our test data. You can see it's the same address as we've got shown just here, and you can see that address F0, F1, F2, F3 here, and now we've loaded that value into A0 here. We've loaded the F0, F1, F2, F3 here. Now this is a little endian system, so of course the value F0 here is loaded into the lowest byte there. So that's typical for little endian. Now what we've done here was load word, so we loaded 32 bits. We've got some other options though. LH will load half a word, 16 bits, and we've got two options here. We've got a load half unsigned, which will load an unsigned number, or load half, which will load a signed number. Now if you don't know, a signed number will need to maintain the negative or positive sign, and the way you do this is you fill any unused bits with the top bit of the value you've loaded. So if you load a half word, for example 16 bits, you would need to fill bits 16 to 31 with whatever bit 15 was, either a 0 or a 1, and that will maintain the sign of the 32-bit number that you loaded in from a 16-bit number. So we're using load half unsigned and load half here. We've also got load byte unsigned and load byte here, and we will see those represented over here. Let's have a look. So we're now loading in these values here. We've loaded in our unsigned bytes, half and byte here. So you can see F1, F0 and F0 have been loaded in here with the load half unsigned and load byte unsigned. And the top bits are all 0 here because we've loaded in an unsigned number. But if we load in a signed number, the top bits will all be the value that was which was the top bit of the loaded value. And because that was an F, in both cases, we filled those bits with a 1, which means that the top bytes have been set to 1s here that were 0s over here. Now, I'm kind of hoping at this tutorial you actually know about signed and unsigned numbers and why that's the case, but just in case you don't, if I change these and I change this to 7-0 and 7-1, well, the top bit will now be a 0, and if I run again, well, now you can see actually that in both cases the top bits are all 0s now, and that's because the sign is now positive of those values, and so now to maintain the sign we fill the unused bytes with 0s. As I say, I'm kind of hoping if you're looking at this tutorial you do understand that, but I know there's going to be a wide range of skill levels and experience, so I totally understand if you don't, but I'd suggest you maybe do some more reading around it because I'm going to rush through that kind of thing fairly quickly in this tutorial. Okay, So that's how we can load unsigned numbers there. Okay, so what we're going to do next is we're going to read and write some data. So we are showing our current test data to the screen, and you can see that just here. There it is. And what we're going to do next is we are going to load a 32-bit word from the test data. The test data's address is in A2. We're loading that into A0. And then what we're going to do is we're going to store that back into our test data address. Now, first of all, we're going to store A2, and A2 contains the address itself. We're going to store A2 back to the memory address in A2, and that's going to change the first value in that address range. And then what we're going to do is we're going to store our test value that we loaded in here, and we're going to store it at the word level. That's of course 32 bits, and we're going to store that to address A2 plus 4 bytes. This is an offset. We can do that in Risc-V, so we're specifying to store that 4 bytes along, and you can see that's actually happened over here. So the first 4 bytes have changed. They've now been reset because we actually loaded the address in, and it's been reversed because of little endian. And then the next 4 bytes are the value that we read in F0, F1, F2 and F3 here. So you can see that has happened, and it's been offset by 4 bytes because we specified that there. We've now specified to store a half, that's the 16 bits of course, at an offset of 8 from A2, and you can see that has happened just here. F0 and F1 are stored, and then 2 zeros, because those bytes have been unchanged. Now, there is only a store half command. There's not a store half signed and unsigned command, because when you're saving data, it really doesn't matter. It's the same storing signed or unsigned values. What we've got finally is store byte, and we're storing that at an offset of 12 from A2, and you can see that just there. There's that 1 byte F0 on its own there. We've stored that to the memory. Okay, so you can see here we can load from memory with the load half, load word and load byte commands, and we can store words, store halves and store bytes. Now, the one interesting thing with these storing commands is the normal syntax is kind of reversed. Usually the source is on the right and the destination's on the left. But in this case, the source is on the left and the destination's on the right. That's just the way it is, I guess. It's slightly odd to me, but that's the way this system works. So that's what we work with. So there we go. We've now learned how to load some values, do some very simple mathematics, and store some values back to memory. What we're going to do finally for today's set is we are going to look at the jumps and some branching. Now, jumping and branching calls, as you would sometimes call them on other systems, is always a little tricky, or a little surprising at least, to people like me who are used to the Z80 and things like that. The way that they tend to work can be slightly odd on these systems with regards to calls. So we're going to have a look at them here, and we'll figure it all out. So the first thing we're going to do here is we're going to do a test of a jump. Let's just run this and we'll see the results on the screen. Okay, so we've got a set of results here, and the first thing we're doing here is we are jumping to the label jump test 1. This J means jump, and we're jumping to the label jump test 1, the label specified by a colon here. And what we're doing here is we're showing the contents of all the registers, and we're showing the message J. You can see this J here, which is just our test to show that this procedure was called. So what we're doing here is we are jumping, and then we are jumping back here, and we've got another jump back here because this is a jump and not a call, so there's no automatic return here. Now in that case we jumped to a label that was specified on the line itself here, but what we're doing next is we're loading the address of jump test 2 into register A0 here. And what we're doing is we're jumping to the address in the register. JR means jump to register, I suppose. And A0, of course, contains jump test 2. And that's this code here, which again shows a message to the screen. It shows JR here. So we've jumped to the register next. Now, these are both just regular jumps. They're not any kind of subroutine. What we want for that is jump and link, JAL. And this is basically like the branch and link command of the ARM. What it does is it will load the return address into the RA register, and this is the return address. Now when we run our jump and link here, we've got this test code here which just shows the message to the screen, but this time rather than jumping back to the running code, we're actually using this return command, and this is actually a sudo up macro, and it is effectively a jump relative to the register return address, which is effectively a return command, or returning to the original call. So that's what we're doing there, and that will return us to the next line here, and you can see that that has occurred here. We've done our first jump and link test there. And then what we've done is we've used the second alternative mode of jump and link, which is where we specify an alternative register to use as the return address. So in the first case, we were using the return regular RA register. This time we're using A1 as the return address. So we run jump test 3B here, which is basically the same as the first one. But you can see here that whereas the first time the return address was 4130, the second time the return address in the RA register has not changed, and the return address has actually been stored in register A1 here. And so this time when we return, rather than using a return command like this, we actually use the JR and A1 as the return register. You see we've used that just there, and that will return using A1 as the return address. And so that's how we return when we specify an alternate address with the jump and link register just there. So that's what we've done. Now the final one that we can use is the JALR command. Now this will actually use a register as the address to jump to. You can see here what we've done is we've loaded jump test 4 into register A0, and we're then jumping and linking with register A0. And again, there is an alternate form of this command, which is this massive long thing here, and we can use that if we prefer to specify the register that is used as the return address, but in this case we're just using this simple one here. And once again we've got our test code here. So in the case of this test, we've shown our JALR to the screen here. The return address is in RA again, which is why we can use that return just to go back to the running code. But this time the address that we called is in A0 here, and the calling address was 400238, and you can see the program counter is 400248 at the time that we showed this text to the screen. So there we go. That's the variety of options we've got for jumping and linking, which would be like your go-to and your go sub in basic, or your jump and your call in Z80, if those are things you're more familiar with. So there we go. We've been over a few of the basics today. We're going to go into some more depth next time. The Risc-V I think is quite interesting. I find it a bit of a shock when I came from ARM, because ARM is surprisingly complex for a RISC system, but Risc-V is a lot more reduced, which was a bit of a shock to me. But I'm told it's extremely powerful, and once I get around the limitations, which we will see when it comes to pushing and popping a lot more, I think once you get around them with some macros and things, it's perfectly pleasant to program for. It's just a shame in a lot of ways that there's not a real system using it yet. I believe the BBC in the UK are coming up with some kids programming device that's going to be using Risc-V, which sounds fantastic, although for some reason it seemed to be quite expensive. It looks like a hand. It's very strange, but anyway, hopefully that will attract some more programming to Risc-V, and maybe more things will come up down the pipeline. I know Risc-V is used very heavily. It's used in things like hard drive controllers, and I believe NVIDIA use them and things, but I unfortunately say at the moment, from the consumer devices point of view, there isn't a lot available that I could use for this tutorial, which is a shame, but I'm really hoping that it will become more popular in the future. Anyway, if you've enjoyed this, please hit the like button, because that helps me with the Google Analytics. YouTube recommends videos based on likes and things like that. And if you liked what you saw, please hit the subscribe, because then you'll see the other episodes that are going to come later on. Of course, as well, go to the website. You can download the build scripts and the pre-configured notepad to run the simulator that you saw today, and you can also download the source code for today's example and the other examples as well, so you can have a go with it all. Anyway, I hope you've enjoyed this. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.